welcome to our data structures midterm review. Hopefully we won't go too overtime here, but we do have a lot of material to cover, but we'll get through this. Yeah. How was you guys' first exam, by the way? Not great? Stressful? Don't talk about it? All right, that's cool, that's cool. But yeah, so this one, typically for a dance student, people tend to do a little bit better, if not the best on this exam out of them all. So we'll be basically in detail cover all these three topics. So we're gonna have the sorting algorithms, stacks and queues, and hashing. And can everybody just kind of introduce ourselves real quick? Let them know. All right. So any questions before we get started? All right, sounds good. Okay, so first we're going to start with the sorting algorithms. So we're going to be covering bubble, insertion, selection, heap, as well as merge and quicksort. Okay, so first let's start with some simple things. So what is bubble sort? Does anyone know what a bubble sort is? Anybody? Where's the marker? It's the slowest sort. You ever heard of BOGO sort? Yeah, bubble sort is essentially a comparison sort that basically you iterate through the array and you compare as you go. So what it does is that basically you compare all the adjacent elements as you iterate through the array and sort them if they're in the wrong order. So we might as well show an example really quick with an array. So tracing is also going to be one of the biggest topics on the exam. So do be aware of how to do all of these sorts. That's going to be my biggest recommendation as you kind of learn through these sorting algorithms. So how a bubble sort works is that first things first, like we said, it's going to iterate through the array, right, as we go. So if we start with the first one, if we're trying to sort this in a ascending order, right, we first look at the first element and we say if it's greater than the second one, then we sort it. So this gets swapped, right? Just like if you see in the first iteration, we see that 5 and 10 get swapped. And then next, we just keep on going, right? So we see that 10 compared to 9 is greater, right? So we just keep on sorting it as we go through. So pretty simple stuff, right? All right, 10 is greater than 3, so we just swap this. 10 is greater than 4, so we just keep on swapping and swapping until we get to the end of the array, right? Any questions with this, by the way? Okay, pretty simple. So you will see something pretty unique with bubble sort is that during the first iteration, and what I mean by that is that it will go through the entirety of the array until it reaches to the end, is that we have the greatest number in the array at the end now, right? You'll see that for every single iteration, for the first one, the 10 gets sorted to the last one. And for the second iteration, since 10 is already sorted, so we don't have to care about 10 anymore, 9 will be sorted in the second last spot, right? Because that's the second biggest number. Does that make sense? So for every single iteration, like the third one, you'll see that 5 gets sorted, so on and so forth until we reach to the last iteration where everything gets sorted. Any question with this? Yeah. Yes. That is correct, yes. No matter where this 10 is going to be, the 10 can be right here. The 10 will be swapped towards the end, no matter what, for every single iteration, right? So for the second one, it'll be the second last, third one will be the third last, and so on and so forth until everything gets sorted, right? So if we see the code for bubble sort real quick, you'll see that for the outer loop, it will be incremented until the very second last element. And why is that, right? Because we don't actually care about sorting the very last element. That thing will get sorted when it happens right here, right? Because it will swap with the last element, right? So with an inner loop, you'll see that it says m minus I. What that means is like when you're actually doing the sorting, right? Like for example, if you get to the second iteration, thank you, you can just set it there, yeah. So when you get to, for example, the second iteration, right, where 9 needs to be sorted here, we don't actually need to care about the remaining anymore because they're already sorted. And that's why it's minus I. Is everybody clear on this, by the way? Right? So with this algorithm, you can pretty much perform bubble sort, right? All right. Feel free to take a picture if you want, but you can also look these up when we upload the slides onto the Discord server as well. But we're going to move on to the next sort then. So what is insertion sort? Anybody know what an insertion sort is? No? If you can answer correctly, I might give you a free pizza. Yeah, what's up? Mhm. Exactly, right? So you first have, we will go to the next slide, sorry. So first, basically it's a sorting algorithm that builds the sorted list, like one element at a time, right? So first you will have basically like a subarray at the front that will be sorted, and then you pick the next element, and you basically sort it within that subarray elements, right? So what that will look like in kind of when you trace through a code, like if I were to show you an example right here, we're going to use the exact same array. Is that I label the next element that's unsorted as a key, right? Because this will make it a little bit more simpler to look at. But if you were to notice, the parenthesis is the subarray that I was referring to that's already sorted, right? The initial array 10 is already sorted by itself, right? Because it's just one element. But if we were to go to iteration 1, you'll see that 5 will be the key, right? Because that's the next element that we would like to sort within that subarray. So because 5 is smaller than 10, right? That's why we're going to have to put 5 at the front, right? Is everybody clear on this? Okay. So next, we're going to look at the next element because 9 is going to be the key that we want to sort now, right? So 9 will enter the subarray, and 9 is going to be at the position between 5 and 10, right? Because that's what the sorted version of the subarray looks like. And what we essentially do is that we look at the next key and the next key and the next key, and we basically sort it in the subarray, so on and so forth, repeatedly until we reach it to the very last iteration. And then everything will be sorted. Any questions on this? Yeah. Loop says for int I is equal to 1. So why is that, right? Because the very first element is already sorted by itself, right? That's why we start at the second one. And what we essentially look for is that we indicate this as the key to start with, okay? And since this is the key, then we need to basically look inside the subarray now, and we say, okay, if this key is smaller than this previous element, we swap it. Does that make sense? Because we need to actually make sure that this subarray is sorted, right? So if it's smaller, then we just say 5, 10, and then this part is done now. That's what happens in the while loop, right? And then when this is done, we still need to keep going, right? So the next one, this is going to be the key now, and this needs to be sorted in here, so on and so forth. And then we keep going until everything is sorted. And that's what's happening in this code. Any questions on this? All right, if not, let's keep going. All right, so next up, we have selection sort. Anybody know what a selection sort is? Nobody? Free pizza. What is a selection sort? All right, so a selection sort is essentially you pick individual elements and you sort it in its correct spot as you go through the array. Okay, so what that's going to look like, if we would just go to the next slide. Sorry, thank you. We're going to use the same array for this one as well, just to keep things a little bit simple. But what that's going to look like is that now we have something called a minimum, right? And what that means is, so first, we know that 10 is already, or sorry, excuse me. So we're looking for the minimum of this array. I'm kind of confusing with the insertion sort here, but so what is the minimum of this array right now? AKA the smallest number in this array. Which one is it? 1, right? Because we know that 1 is the smallest element. All we have to do is essentially we just swap it with the first one. Because we know that that's where 1 needs to go, right? So what's that's going to look like is 1 is going to get here, and then 10 is going to get swapped at the end. So 1 is done now. This is like the sorted part, subarray, similar to how insertion works, right? And then next up, what is the second or second smallest number in this list? 2, right? So 2 gets swapped by 5, right? So what that's going to look like is 5, 3, 4, 10. And you do this so on and so forth until you reach to the very end of the list. Any questions on this part? All right, if not, We can go to the code real quick. So this one is probably the very most simplest code that you could probably see so far, but essentially, just like how we kind of explain how the logic goes, you go through the array and you ignore the very last number, because then again, we don't actually have to care. When we actually reach here, then we know that these two, if they somehow get swapped, right, this is already going to be correct. So we don't need to sort until the very last element. Excuse me. That's why it says I is smaller than n minus 1. And then we look for a min index is equal to I. And what that's going to track is that we're essentially going to try to find in the array which one is going to be the smallest number, right? Once we find it, min index is equal to j, then we just essentially perform the swap. And that's it. Okay, until we reach to the very end of the array. Any questions on this? All right, if not, we can keep going then. All right, so this is going to be one of the tougher sorts, right? Heap sort. Anybody know what a heap sort is? Any brave souls? No. Exactly, right? So if we go to the definition real quick, yes. So what will look like is that we basically first start with a binary heap structure. It's going to be like a little binary tree, okay? And essentially, we need to perform something called a max heap, which I'll explain in just a moment. And you swap from the parent to whichever number that you need to swap, and then you build onto the array until everything is sorted. This might sound a little bit complex, but just bear with me, and I'm going to show you an example with a with the example right here. So we're going to do a little bit differently this time with a different array. Okay. So first, if you're unfamiliar with a binary tree looks like, essentially all it's going to do is that we have a parent at the top, and then we have two children at the bottom. So first, we need to construct this tree. Okay. So we have 2 at the top, and then we have the first child, which is 5. I'm just going over this array right here. 3, 9, right? So every parent has 2 children, so 1, 4, and then 10. Okay? So first, like I said, we need to construct the max heap. And what that essentially means is that we need to go to the very last parent of this heap structure first. And then we need to swap with the maximum number within that parent and children relationship. So what is the very last parent within this heap right now? Which number is it? Does anybody know? Yes, it is 3, right? Because 3 is the very, very last, because if you look at all of these, they don't have any children connected to them, right? They don't have any child nodes connected to them. So that's why 3 is the very last one. Okay, so if we look at this 3 right here, which one is the largest number out of these 3? 10. So then all we have to do is swap 10 and 3. Okay, because we know that this is the largest number within this little parent and child relationship here. Okay, and then we do this over and over again until we reach to the very, very first parent. So next parent we need to look at is this one, right? What is the largest number between these 3 numbers? 9. That's correct. So we need to swap 9 with 5, right? And then what is the very first parent right here? It's going to be right here, right? So what is the largest number out of these 3? 10. Exactly, right? So 10 gets to be on the top. And I'm actually going to write this again just because there's too many circles here. But 10, 9, 2, 5, 1, 4, 3. And this is what we call a max heap. Okay? So this structure right here is what we call a max heap. Now afterwards, obviously this is not sorted, right? Because the sorted array is not going to look like 10, 9, 2, 5. That's obviously not sorted. So what do we go from here, right? So next, essentially what we need to do is that we know that the very largest number is going to be at the top now, no matter what, because that's how the max heap algorithm works, right? You basically pick the very largest number to the top. And then the smart thing about this is that essentially you just need to sort, or not sort, but swap the very largest number with the very last element, okay? And just bear with me on this. So 10 gets swapped with 3, okay? And then we know for sure that 10 is sorted now because it's at the very last element. It's the largest number, right? But we don't know if this is the largest. That's why we need to perform something called heapify, okay? And we're going to discuss the code in just a moment and how this thing actually works. But so what that means is that you're going to need to do the same thing with whatever we just did with this parent right here, okay, recursively. And also, I actually missed one thing real quick. Sorry about this. But so while I was actually doing this max heap structure, I forgot to include the fact that when you perform a heapify with this 10 right here, right, we swap the 10 and the 2, but this 2 actually needs to be taken care of as well, or all of these parents, because it's a recursion, right? So if we would check the parent and child relationship between these three numbers, we know the 9 is the biggest, so we don't have to care about that. But in here, actually, 2 is not the largest number within this structure right here, right? So we need to swap 4 and 2. So sorry about that. I did actually miss that. So if I were to swap this real quick, so 4 and 2, right? So that will be actually the max heap structure with 10 being on the top and then 3 on the bottom. So I do apologize for that. But so if we were to keep going, so again, we need to perform the heapify on 3 now, right? So what is the biggest number within these three? Well, we know that 9 is the biggest number, right? So we can just swap 9 with, or sorry, with 3, right? Okay, so now we need to make sure that, again, recursion, right? So we need to make sure that this 3 is the largest number out of these 3, which is not, right? Because 5 is going to be the largest, so we can swap 5 with 3. So 5 is going to be right here, and 3 is going to be right here. And if you do this step over and over again, no matter what, you're going to get the largest number out of the unsorted list at the top. And then once this step is finished, you just have to swap this 9 with the second largest number now. So then it would just be 2 right here, and then 9 right here. And then we know that this is going to be sorted. And then you keep on repeating this process until the entire thing is sorted. Does that kind of make sense to everybody? Yeah. Basically, yes, yeah. So if we were to actually go to the code real quick, this might look very complicated, but we have a heapify function first, right? So what that's going to do is that you'll see this very interesting algorithm that calculates the left and the right, right? What that's actually calculating is that if we were to look at this largest equal to I, and then we start at the half of the array. Why is it half? Because that's actually a very clever way to calculate the very last parent. Because you'll see that int I is equal to n divided by 2 minus 1, right? Because if we were to do this, 1, 2, 3, 4, 5, 6, 7, there's 7 elements in this array, right? If we divide it by 2 and then minus 1, because that's the algorithm, this will get you 2, right? And then if we look at the index for this, it's 0, 1, 2. And that's the first parent that we need to take care of. And then we do this heapify function over and over again until we reach it to the very top, right? Because we need to go from 2, 1, 0. And then we do this heapify for all 3. Just like what we talk about, right? All we're doing is just swapping with the largest number, move it to the top, and then we just basically swap these 2 and then do heapify again for the very top number. And that's exactly what this thing is doing, right? So first, the very first for loop is constructing the max heap. And then afterwards, we're just performing the entirety of the heap sort. Any questions on this? Yeah. Mm-hmm. Because so this, in terms of an array, right? This right now would look like 10, 9, 4, 5, 5, 1, 2, 3, right? So we know that the 10 is the largest number at the top now. We need to swap the 10 at the very last number, right? Because we know that this is the largest number. Does that make sense? So that's why we swap. This is how it's going to look like in an array, right? 3 gets here, and then 10 gets here. And then we do this very intricate algorithm to perform heapify on 3 now. Obviously, we can't really see this in an array because that's very difficult without actually drawing this out. And that's why I kind of left all the visuals on the slides, but rather draw it out on board because it's a little bit easier to demonstrate, right? Saw a hand raise up. Is there a difference between the max heap? No. Mm-hmm. No. So heapify actually does the exact same thing. Yeah, because so heapify, all it's really doing is, again, it's like just comparing which one is the largest number within that little 3, relationship, right? And then you just keep going until it reaches the very top, because it's a recursive function. And if you were to kind of read this code a little more explicitly, you'll see that all it's doing is just swapping until it reaches the very top. And then once you have the largest number at the top, again, you just swap, right? So this thing will actually cleverly work for not only just the max heap structure itself, but also heapify itself. It's the same exact thing, right? Yeah. Any other questions on this? Alrighty, if not, we can go on with the merge sort. And I have another one. Yeah. Oh yeah.
Okay. I'm going to talk about merge sort. Does anybody want to give it a shot? Guess at what merge sort is or does? Half of it's in the name. All right. So merge sort basically just keeps it recursively divides the array in half each time until you get it into like the singular elements, and then it recursively sorts each single element by joining them together. Uh, yeah, and this is done using two functions. One of them recursively divides it, and then the other one sorts the arrays together. Yeah. All right. So let's do an example with the same array that we've been using. All right. I hope y'all can read this. All right. So the way it does, you can skip to the next slide. As you can see, it's going to split it in half. And the way you split it in half, and you get these, and then it's just going to recursively do it until it's just literally singular elements. And then basically going to continue with these. And the way the algorithm is, it just leaves this one out till later. And so these two elements are combined and sorted. And then these two, and these two. This one's still one. And then it joins these two. And then the way that the algorithm in the function, it will sort itself whenever it's combining these two. So it's these two, right? Yep. So 1, 3, and 4, and then in the end, you get the sorted array at the bottom. And yeah, you can go into the code. It looks complicated. So you first start with the merge sort, and as you can see, you get the middle element by doing I plus k minus I divided by 2, and it calls itself again using the first half and then the second half, and then it's just going to keep recursively dividing itself till it gets to these singular elements. And then at the end of each recursive call, it's going to call this merge function. Looks crazy. This is what's sorting it. And then at the end, it merges them all together. Yeah, it looks complicated, but it's just comparing them and then making sure it's sorted. Yeah. Any questions? Yes. It's just as you can see in the first line, it's gonna be I, which is our first index 0. I think this is size 7, so it's gonna be because it's gonna divide it in half each time, right? And so the way it does it here, 7, 0 plus 7 minus 0 divided by 2. That's gonna return 3 because these elements are ordered 0, 1, 2, 3, 4, 5, 6, and then we send the first half from 0 to 3, and then the second half, your j plus 1, which is 4, all the way to 6. Any other questions? All right. All right, so now we go on to quick sort. Anybody want to take a guess at this one? What quick sort does? I'm sorry? Huh? Yes, you do. But what do you do with the pivot? Where do you go on from there? All right. Basically, you choose a pivot. This could be any pivot, a random one, the first one, the last one, the middle one, whatever. And then you're gonna organize the rest of the array as you're gonna have less than pivot, pivot, greater than pivot. And it's gonna keep doing this because each side It's going to be reducing the size of the array. And at the end, you're going to get the singular elements all ordered. And then it's just going to join them all together, and that's going to be your array. And yeah. Let's do it with the same example. And here we're using the pivot. Always going to be the first element of the array. Go there. This one has a little bit of a typo, but that's okay. And so we're going to have our pivot as 10. And so you're just going to go through the entire array, sorting it. And you're going to, the less than and greater than pivot arrays, they're going to be in the order that it comes in. It's not going to be sorted already. So 5, it's less than 10. I'm going to add it over here. 9 is less than 10. 2 is less than 10. So it's 3, 4, and 1. So you have your less than, your pivot, and your greater than. It's going to be empty. That's okay. And you just keep going that way. So now we have pivot is 5. All right, 9 is greater than 9. Let me these to separate them. 9 is greater than 5. And then you get 2. 2 is less. 3 is less. 4 is less. 1 is less. And then you go again. 2. 3 greater than 2. So it's 4. 1 is less. And so yeah. So here is singular element. And then so we're gonna move on to the greater pivot side. Your pivot's gonna be 3. 4 is greater than. And yeah. And so basically you're gonna have your 1, your 2, your 3, your 4. This was a bad layout. But yeah, you're gonna have, where did I put it? Up top, it's gonna be all singular, but here merge them together. Yeah, this is not a good way to write it. That's a good way to understand it. You're just gonna have a side with less than, a side of greater than, and at the end with the individual elements, they're gonna be all sorted, and it just combines them. Any questions? Okay, we can move on to the code. This one's also done with 2 different functions. So the first one, where you partition it given an element, okay, or pivot, I think, one of them. And so you're gonna be partitioning them. Oh, never mind. Yeah, this is done with 2 functions. You're gonna call quicksort first, and then you're gonna be given the a j value after calling the partition function with the starting value and the pivot. Never mind. The start and the end value, that's what it is. And yeah, it's gonna take care of it by itself. It's a little confusing, this one too. Yeah. Any questions? Hopefully I can answer them. Okay. So now let's move on to the time complexity. There's a lot of them on here. You don't need to know all of them. The only important ones are going to be the ones that we talked about. Let me write them down. It's a little bit easier. You're going to have quicksort as n log n. Most of the time, as you can see, there's going to be a different one for best and worst. Quicksort's the only one that has a different average one from the rest. Well, actually, no. It's the only one that matches the best case. So yeah. So with the way quicksort works, the reason... Yeah, that's good. Okay. The reason with quicksort is that the way an array gets the best time complexity is that whenever it's splitting the array, is that it's splitting it equally. So as I don't know if y'all remember from the first one, all of these elements were less than 10, and so you had like n minus 1 less than pivot, then your pivot, and then your greater than pivot was just empty. And so it's going to be keep the n minus 1 gets divided more times than an n divided by 2. And so that's how this one is a bad case. And then you have merge sort. Merge sort is special. The best, average, and worst is going to be the same, because the way that it works is that it's going no matter what your array is, it's going to keep dividing it, even if it's already sorted, even if it's in decreasing order, if it's random order, the same one each time. And then this is a lot to write down. Never mind. For time's sake, so yeah, so quicksort. The time complexity is going to depend on the pivot and if it's splitting the array in equal parts. Merge sort, it's going to be the exact same n log n no matter what, because no matter how the array is formatted, it's going to be divided in half. And then heap sort. Heap sort is also the same because it's going to make a tree. And then bubble sort, it's O of n, or whatever. What? Best is O of n, and then worst is O of n squared. The best case is if it's already sorted, because then nothing needs to get swapped. It's kind of just iterating through the array just to make sure that it's sorted already. Same thing with insertion sort. Best case is going to be O of n. Worst case, O of n squared. If it's literally in decreasing order, then everything needs to get swapped. And then insertion sort. I already talked about that. Selection sort. Worst one of all, n squared, no matter what. Yeah, there's a good table. You only need to focus on the first two and then the four after. Yes. Yes. You had a question? What do you mean? Like give the best time?
It will insert average, but they will probably specify which one they want to
Picture.
I will highly recommend writing this somewhere.
Oh yeah, definitely write it.
Yeah, so this is really good stuff you have to memorize.
A lot of ends and logins to memorize. I think on the exam it'll probably tell you which one to use,
So
but
there's no right or wrong answer for that, but it's just like all these different types of
like obviously you don't want to choose one that's like n factorial, but like yeah, you'll be given one.
a little bit of a collaborative question. We're kind of running out of time, so if you would just kind of scan it and just go through. You guys can try it on your own first, real quick.
All right. Let's start off with the first one. Quick sort. Given the array 4, 2, 6, 1, 3, 5, and 7. Oh, thank you for putting that in. I forgot to put that in. Where the first element is a pivot. Has anyone figured out the answer or any guesses? No, it's okay. So yeah. 4, 2, 6, 1, 3, 5, 7. 4, 2, 6, 1, 3, 5, 7. Okay. And the pivot's the first element. So we're going to start off with 4. And we're going to break it down with 4 in the middle. And then 2 is going to be less than 4. 6 is greater. 1 is less. 3 is less. Not a 3. 5 is greater. 7 is greater. See? As you can see with the difference of the first example that we did, this one's evenly divided. And so already we're doing better. Like this one's already like half the size. So is that one. And then if we continue, we start off with 2. 1 is less. 3 is greater. We got 4. And then 6. 5 is less. That's not a 5. 6. And then 7. And that's already sorted. And that only took like 2 pivots. And so that's the best case time complexity. That was the answer, though. I think it was n log n. All right, so that's for quick sort. Really depends on where you put your pivot element and how it divides the array into less than pivot, pivot, and greater than pivot. 8, 7, 5, 3, 1. All right, so this one was bubble sort, and hopefully y'all were able to tell right off the bat. Any guesses on what the time complexity was? Yes, this is literally the worst case where everything was in descending order, and so everything would have to be swapped multiple times. Moving on to the third one. Version 13.5.7.2.1. This is literally the same one. It's in decreasing order. Insertion sort is better when it's already sorted in increasing order. I think this one was n log n or n squared? N squared. And then the final one was merge sort. And I don't even have to write this one because merge sort, no matter what array you're given, best, worst, average, it's going to be n log n. Any questions? Right? Yeah, that diagram's super useful. Write it on your cheat sheet. Yeah.
Anybody still need this image to take a picture of? All good?
Okay. So this is stacks and queues. Does anybody know what a stack is? Anybody? Okay. A stack is last in, first out, and it's a linear data structure, and then you can only access the top. Right, so some applications are, there's prefix, infix, postfix, expression, conversion and evaluation, memory management, and syntax checking. Functions from the STL are push, pop, empty, and size. So first, we have an example. Given a stack of unsorted integers, create a function that uses another stack to sort the unsorted stack. So I'll go ahead and trace this out. So we have a stack here. So we have 2, 5, 4, and 3. So this would be our unsorted stack. And then we'll have a new stack called sorted. And so what you first want to do is pop the top off and then save it. So that would be called top equals 3. We'll go ahead and pop that. Then we're going to immediately push it and just skip the second while loop. So we'll go ahead and push it in the sorted stack. The next thing we want to do is pop off 4. Now top equals 4. And then we're going to compare the top with 3. So 4 and 3. 4 is greater than 3, so we can go ahead and push it in. Next, we'll go with 5. 5 is greater than 3, so we can go ahead and push it into the sorted. And then lastly, we have 2. So now top equals 2. And then 2 is less than 5. So then I just realized I was doing this backwards. Okay. So it's actually supposed to be, let me see. Give me 1 second. Okay. So we're comparing the top of sorted to top. Okay, so we're pushing 3, and then 3 is less than 4. That's false. Wait. So this is true, and sorted is not empty. So we're gonna go ahead and push 3 back into the unsorted, and then push 4 into sorted. So after that, we skip the second while loop, and then push 3 in. Now we pop off 5. 5 is greater than 3. So what we want to do is we want to keep pushing the sorted into unsorted. So we push 3, and then 4, and then we push 5 into sorted. And then we can keep pushing 4 and 3. And then the last element is 2, which we can skip the second while loop and push on. And then that will be your sorted stack. Okay, next slide. What is a queue? First in, first out, yes. All right, it's a linear data structure, first in, first out. And then the first element in the queue gets pushed out. And then some applications, task scheduling, process synchronization, printed queues, functions, enqueue, dequeue, empty, and size. So this one, given a queue, reverse the queue using recursion. So we'll go ahead and trace this. So the base case, if the input stack is empty, we'll return it. And then for each element in the queue, we'll save it and then do a recursive call. So this would be so for the first iteration, we save 5, and then we call a recursive call. So now we'll go to the second iteration. Front equals 4. We pop. Third iteration, front equals 3. And then the last iteration, front equals 2. And now the stack is empty, so we'll go ahead and start pushing. So now, this is the same queue. So then we push 2, push 3, push 4, push 5, and now the queue is reversed. All right. Now, what is a priority queue? Okay, a priority queue is a queue that's arranged by priority. So it's not necessarily first in, first out. It will be arranged. Okay, so we're going to write a function that enqueues an integer for a priority queue. And the larger the integer, the higher the priority. Okay, so what we want to do is first, we want to check the first value, the front of the queue. So if the front of the queue is smaller than the value, then we could just immediately push the value, then iterate through this loop that gets to the front of the queue. We have front equal the highest value and then keep pushing till we're there. And then if that's not the case, we'll do a for loop to traverse the whole queue and push the value when we need to. So for example, front, 4, 3, 2, 1. We'll do. And we want to push in 3. So we skip the first if statement since that's not true. And then we'll iterate. So we'll pop 5 and then push it. We'll push 5 and then pop it. Now it looks like this. And then the next iteration, we compare 3 and 4. We gotta push 4 to the back and pop it. And then lastly, we compare 3 and 2. And now we can push it to the back. Now the new queue, 3, 4, 5, 1, and 2. And then lastly, we have to get back to the front, so we just keep pushing it to the back and popping it off. Then we get 5, 4, 3, 2, 1 after the last traversal. Okay, any questions? Okay. And then the last slide is the big O for all of the template functions for stacks, queues, and priority queues. The insert, delete, search, push, pop, size, empty. Most of them, for push and pop, it's O of 1, except for priority queues, it's O of n. And then size and empty are also O of 1. And then to search, it's always O of n. O of 1 for insert and delete, O of n. O of 1 for insert, delete, O of n for priority queue, insert. Okay. Any questions about this slide or at all? Awesome.
All right, so now we're gonna go over hashing. Anybody have an idea what hashing might be? Or what a hash table is by any chance? What is it? Yep, that's basically the idea. So basically, when you hash something, you take in a key, and then you pass it through a hash function, and then you get an index, right? That index will tell you where the key, because if you go to the next slide. So yeah, basically, hashing is just the process of turning a key into a hash index through the use of a hash function. So what you explained was basically the hash function, right? You take your key, you take the modulus of so it's the key modulus table size, and then that gives you the index, right? So basically, you take that index and then you store that key, and like basically we store it in key pair values. As explained right here, we have a hash table that holds key value pairs, and the key is your identifier, and the value is the actual content that you're storing there. Okay. Whenever we are dealing with indexes and going through the hash function, we encounter collisions. And if at any point we do encounter a collision, we need to find a way to handle it. So a collision occurs whenever 2 or more keys are hashed to the same index in a hash table, right? So I think this will be easier to explain whenever we go through the examples, so just move on. All right, so the first hashing method we have is direct hashing. Anybody know what direct hashing is? Top of the head? Yes, that's exactly what direct hashing is. So
if here's the code that we have, right? So the index is just found by doing key modulo table size, right? So we could do something like this. Okay, so right here we have our hash table of size 10, right? So let's say table size is equal to 10. If we were to do direct hashing on this input values of 2, 22, 12, and 32, if we do 2 modulus 10, we're going to get 2, right? So now 2 is going to go right here. If we do 22 modulo 10, we're going to get 2. So direct hashing does not have any collision handling. So what's going to end up happening is that the 2 that we have in index 2 is going to get overridden with 22. So as you can see, we have 2, 22, 12, 32. All of these, the remainder is going to be 2 if it's divided by 10, right? So the only thing that gets kept in this input values is just going to be 32. So as you can see, we lost 3 pieces of data. So direct hashing, the main drawback is that there's no collision handling. It just overwrites, so you lose a bunch of data, right? So we can move on to the next one. All right, so this is our first function that takes in that we use to deal with collisions, and it's called linear probing. Anybody have an idea what linear probing is? All right, so basically we take the same idea that we got from direct hashing, and you're gonna see it that it's consistent throughout the hashing methods that we do. We find our index by doing key modulus table size, but this time we include I. Does anybody know what I would be in this case? So if at any point we do encounter collision, we will look for the next open spot, right? So our I is incremented by 1 until a free spot is found. So if we have the same example that we use, right? 2, 22, 12, 12, and 32. Our first one, the remainder is going to be 2, so we can put it at 2. And then if we do it again for 22, we're going to have the remainder of 2, right? So we're going to have collision for index 2. So therefore, if we look at the code, we go again, but this time we're going to increment I by 1, right? So now our I is 1 instead of it being 0. So it's going to be 22 modulo 10, which is 2, and you add 1. So that index is going to be 3, right? So now a 22 is going to go right here at 3. So as you can see, it's just linearly looking for the next available spot in the array or the hash table. So in this case, what would be the index for 12? If it's looking for the next open spot, which one would be? If our previous one was 3, what would be the next open spot? 4, yes. So it would go, 12 would go there. And then the next one would be 32 at index 5. So that's the basic concept of linear probing. It just looks for the next open spot from wherever the collision happens. Right here, our collision is happening at 2 because all of these have a remainder of 2. So the collision is happening at 2, and then from here, we linearly look for the next open spot. Okay? And yeah, that's all. Move on to it. Okay, and now we have quadratic probing, which is somewhat similar to linear probing, but this time we look at it quadratically, right? Whenever you think about quadratic, is something to the power of 2, right? So in this case, we find it by multiplying our I times another I, right? So I times I, which is I to the power 2. So you're just doing that until you find an open spot. And then we could go over an example by hand. So let's just do 2, 22, 12, 32, right? So first one, 2 modulo 10 is going to equal 2, right? Are there any collisions at 2? There's no collision, so we're going to go ahead and put 2 in index 2. All right, now we're going to do 22 modulo 10 is going to give us 2. There's a collision at 2, index 2, because we already have a value in there. So we're going to go ahead and do it one more time, right? So now we're in iteration where I is equal to 1, right? So we're going to do 22 modulo 10 plus 1 times 1, right? So this is going to give us 2, and then 1 times 1, that's 1. So our index now for 22 is 3. So 22 goes into 3, right? Now we're going to go to 12. 12 modulo 10 is going to equal to 2, right? There's a collision because there's already something in index 2. Now let's do 12 modulo 10 plus I times, well, in this case, 1 times 1, because our I is 1. And now this is going to equal to 2. This is going to equal to 3, right? So collision at 3. Do it again. This time our I is 2. So now it's 2 times 2, right? So this is 2 plus 2 times 2, that's 4. So it's going to equal to 6. So at 6, there's an open spot, so we can go ahead and put 12 and 6. And that's the basic concept. So again, we're going to have, since all of these have a remainder 2, 32 is going to have a collision for here. So it's going to move to here, and whenever I is equal to 1. And then it's going to move here whenever I is equal to 2. So in this case, it's going to be 3 times 3, which is 9, right? Plus 2, it's going to be 11 modulo 10. So it's going to be a remainder of 1. Because that's why we have that extra table size at the end, is to make sure that it falls within our table size. So in this case, 32 is going to go at 1. Okay. Does anybody have any questions with quadratic probing? Do you guys get the general idea? Okay. There's no questions, then we can move on to the next one. And that's the code. I haven't explained the code yet. So for all of these hashing methods, they're kind of the same thing. The way that we include to find the index with I, we go through a for loop. And if at any point there's a collision, then, well, first we check if at index, if it's empty. If it's empty, then we insert the key into that index. So we're basically doing that until we find an open spot. And we use break to break out of the loop. So we don't constantly insert into an empty spot. So anybody have questions on the code? Any particular parts? Okay, so double hashing is a little bit different. And double hashing, we just have 2 hashing functions. So if at any point there's a collision and in our insert values, if our keys result to the same index, then we're going to use another hash function. And the other hash function is prime number minus key modulo prime number. And the prime number is the greatest prime number that is less than your table size. So in our example, we're using 10. The greatest prime value would be 7. Okay, so we can move on. Yep. And then you do an example for this one, because this one's a little bit complicated because you have 2 hash functions, so it's a little bit different. But as you can see, we do our hash 1 function is just direct hashing, right? So all we're doing is key modulus table size. If at any point we find a collision, then we're going to do hash 2, right? Which is the prime number minus key modulus prime number, right? So in our for loop, if we find a collision, then our I is going to equal to 1 because it's going to move on to the next one. And then we call hash 2 in that case. All right, so let's just trace it by hand really quickly. Let's do the 2, 22, 12, right? So looking at the code, or how we find the index, right? Let's do hash 1 is equal to 2 modulus 10, because our table size is 10, it's going to equal to 2. So 2 goes into 2, right? Our hash 2 is not being used. It's not going to be called because in our first iteration, our I is equal to 0, right? So it's going to be 0 times a number. It's just going to be 0. And then yeah, it's going to be 2 modulus 10, right? So if I index 2, if it's empty, then we insert a key, right? So that's all we're doing here. So we didn't have to call hash 2 because there was no collision here, right? So now let's do 22 modulus, what is it? Modulus 10, 20 equals 2. So we have a collision here. So in this case, we are going to have to use our second hash function, which is prime number minus our key modulus prime, right? So what's our greatest prime value in this table that we can use? So we have our table size is 10. We want the greatest prime value that's less than 10. So it would be 7, yes. So our prime is going to equal to 7, right? So let's just use this function right here. So 7 minus our key, in this case is 22, modulus 7, right? So 22 divided by 7, that's going to give us a remainder of 1, right? So 7 minus 1 is going to equal to 6. So, and then our index is found by hash 1 plus, so our hash 1 is 2, plus our hash 2 value, which in this case is 6. So 2 plus 6 is 8, modulus 10, because we have a modulus on the outside, and equal to 8. So now our 22 is going to go to index 8 right here. So this is where 22 goes. Okay. Now let's do the same thing for 12. We already know from the previous examples that we're going to have a collision at 2, right? So we can calculate our using the hash 2 function, right? So our hash 1 is going to equal to 1, it's 2, right? Plus, what's our hash 2 value? Let's do, it's 7 minus 12 modulus 7, right? So this is going to be 4, because 12 divided by 7 is, yeah, it's 5, my fault. So 7 minus 5 equals 2. So that's the return value from hash 2. So it's 2 plus 2 modulus 10, right? In this case, it's going to be 4. So our 12 is going to go right here. Okay. Yes. So if your table size is going to be given to you, so your table size can vary. So if at any point, like if it's less than 10, then you would just calculate it from there. It's just the greatest prime value that's less than your table size. That's how you find your prime number. Okay.
Like a formula to find that, or do you have to like kind of know?
In my case, whenever I took the exam, they just they give you the table size, so you just find it yourself. Yeah. But I'm pretty sure you can find a way to automatically do it, but you don't have to do it for the exam. Okay. Any more questions on this? Okay. Okay, and then the other method that we have is separate chaining. All this is if there's a collision, well, each element of the hash table is going to be a node that points to another node. So this is basically going to be linked lists that connect to other nodes here. So yeah. Okay. So in our example, we have 2, 12, 22. Obviously, we're going to have 2 collisions here, right? Our 2 is going to go to 2, right? And then 12 is going to give us the remainder of 2. So what is going to happen is it's going to link to another node with the value in here. So if at any point there's a collision, all it's going to do is basically connect that value to the list that's already in that node. And I think it's better if you can move on to the next slide. Yeah. So we first start with a temporary node. This is going to be our new node that we get from this. And then so the way that it initially starts is that they're all null, right? So what the first if statement is saying is that if at index it's empty, if it's empty at index, then just basically put our temporary node, right? Just the address to be here. So in this case, it's gonna be temp. Temp is gonna be right here, right? So now this one's not null, right? So if at any point that it's not null pointer, then you basically just iterate through this until you can until you link it. So you're just traversing a linked list, but basically an array with linked lists inside of it. Okay. So in our example, we had 2, and then there's a collision at 2 again. 12 goes there, and then 22 goes here. So if you're tracing it by hand, this is how you can show it off. So anywhere there's a collision, you just add onto the list at that collision index. Okay. Any questions on this one? Okay, we can move on to the next one. All right, so now we can go over what a map is in C++. Anybody knows what a map is? No? Okay. So a map is basically it's just a container in the standard template library. They store the values in key and map value pairs, right? So a key is just used to identify your value, and then your map value is just simply your map value is just simply your data. So the data that you want to store, right? So it's the actual data. Right. So we can move on. So here are the attributes of a map. They store elements and key values pairs. Each key must be unique. So if they're not unique, then you can't find your value basically. So each key must be unique. Maps sort based off your key. You access your values through using the bracket operator. I will go more in depth in that in the next slide. And in C++, the maps are usually implemented as trees rather than arrays. And the time complexity for all operations is it should be O log n. That's a typo, but we can move on. Okay, so let's look at this code. So at the very top, we're doing include map, which this brings it in from this brings us the map container from the standard template library. And then right there, we have map, int, and string, and its name students, right? So let me go over this really quickly. So we have map, int, string. Okay, so all we're doing here is initializing our map, right? Or creating a map, right? So this is our container. This is our key. So all of our keys, they're gonna be of the integer data type. And then our values are gonna be of the string data type, right? This is our value. And this is just simply the map name. Right? So that's what we're doing at the top right there. So they're stored in pairs, right? So you have a integer string pair. So your keys are they can only be integers, and they must be unique integers, right? And our strings our values are strings. Okay, and then the way you insert into a map is by using the bracket operator, right? So you insert into the map that you want, so you call it by the map name, right? And inside the bracket is going to be your key value. So remember that your key is used to identify your map value, right? So you set whatever the key wants to be, right? So in this case, it's 567, I think. And then, so now this key is going to be attached to whatever string that you have over here, right? This case is John, right? So our key value pair is, in this case, is 567. And then we have the string John, right? So if at any time you want to access the value that's attached to 567, it's going to be, you just use this notation right here. So this is how you access the values. By inside here, you just put the key. Okay, and then in the code, we just keep on inserting. We insert two more values into it with unique keys. Remember, that's one of the main attributes. And then whenever you want to access it, you access it by the key, right? So in that case, on the cout statement, the first cout statement, we're just outputting the student with the key value of 101. Okay, so what if we change this statement to students 880? What would that output? Does anybody know? Yeah. So the key that's attached to Michael is 880. So the output of that is going to be Michael. Okay, and if you ever want to iterate through the entire map, that's how you do it. And yeah, that's all for this. And the output is sorted by key. So remember, whenever you're using maps, the output or the keys are sorted, right? So in this case, they're sorted in ascending order. Right? So it's 101, 567, and 880. And that's not how we inserted it. We inserted it, or 101 was inserted the second time. So, and our output is the very first output. So, yeah. Any questions on this? What's your map stuff? You taking dance? I'm not sure because I took risks, so I'm not sure. We didn't have maps on there, but you guys might have maps because, yeah. I don't know what's on the exam. I'm gonna be honest. Okay. Yeah, but just try to understand it. It's a really simple concept. Just look over it. It's just a different container. It just accesses things with key value pairs. That's it. That's all you have. Okay, so you would want to know the difference between a hash table and a. Well, let me go over this. So if at any point you hear the term hash map, this is equivalent to saying a hash table. Okay. So whenever you're using hash tables, they still store it in key value pairs, right? In C++, the hash tables or hash maps, they're usually implemented as arrays rather than trees. Remember with so this does not equal a map, right? So these are two distinct values, two distinct meanings, right? So in our maps, they're usually implemented as trees, whereas our hash maps or hash tables, they're implemented as arrays, right? So in hash tables, we do use hash functions to calculate our index for the array, for the hash table. And you do need a collision handler if you're using hash tables. The main part that's good about a hash table is that it has constant time complexity on the operations. So I don't know if you guys remember, but a map had O log n, which is slower than constant. In this case, O1. So if you prefer it to be, if you prefer a fast operations and you don't care about the sorting, because remember whenever we hashed, it was all over the table. So like if you don't care about the keys being sorted, then you're best off using a hash table. And if you want to use it in C++, you would use it. It's called an unordered map, basically. So the STL container is unordered map, and that's how you import it into your code. Okay, and then go to the next one. And then now we have maps, which is what we went over before that. They still stores in key value pairs. All the keys, they're sorted by default. They're usually implemented as trees, so the time complexity to search through that tree is going to be slower than an array, because whenever you have a hash table, you get the index and then you quickly access the value, right? Whereas in a tree, you have to traverse the entire tree to get that value. So that's why it's slower. And there's also no need for collision handling because you're not calculating an index. You're just inserting it to a tree. And kind of on that topic is, it would be a binary search tree where your parent values, they're greater than your children. So if we had 10, 21, and 9, right? Our parent's going to be 21. Anything to anything to the left side of the parent would be less than 21, which in this case is only going to be 10. Anything to the right is going to be 30. Anything here is greater than 21. Right? And more on this, you guys are going to learn more about this whenever you guys prepare for exam 3. So don't think about it too much. But that's the general idea of a map compared to a hash map. So yeah, so if you care about your keys being sorted, or you don't care about the time complexity, then go for a map. Okay. Any questions on hashing methods, hash tables, maps, hash maps? So let's say let's say you have a string, right? And you want to find out the frequency of each letter, right? So you could use a map. If you don't care about the order of your keys, then you would use an order map. So okay. So let's say let's go step by step, right? So we don't care about the order, right? So we're gonna use an unordered map, right? So what would be our key value in this? We want each individual character. We want to find the frequency of each character. So in this case, it would be character int, right? Yeah. So char int, right? Call it frequency. All right. So frequency, right? And then you're simply just gonna iterate through the string, right? And then just it's gonna be basically frequency. It's gonna go by character, right? So in this case, it's gonna be A. So whenever it's the first iteration is gonna be A, and then you just do plus plus, right? So that's gonna increment the value. So in this case, it's gonna be 1, right? So we have first iteration, we have 1A, right? And then second iteration, this is gonna change to 2. And then third iteration, B gets added to the map, right? And then that gets 1. And then that goes to C, gets added to the map, gets 1. And D gets added, and gets 1. And then you iterate through it, and then you can find out the frequency of that character per string. Yeah. So a lot of questions on LeetCode. If you're doing LeetCode, you can use maps. So it's a pretty helpful data structure to understand. Yep. Any more questions? No. Yep. Well, that'll be all for, and that's just a quick summary of the differences between those two. But I already went over it. Oh yeah, there's problems, right? If you guys want to work together and work on these problems, they're just tracing using the different type of hashing methods. So I don't know if you guys want to go over that right now, but yeah, we got this. We got problems. That's the answer.